In this topic, we're going to be having a look at momentum and impulse. All of it is based around Newton's third law of motion, which says that when two bodies collide, they exert an equal and opposite force on each other. So from this, it means that it also exerts an equal and opposite impulse on each other. And that's almost a different way of thinking about a force. So what we're looking at this time is the change in momentum of the particle. Obviously the particle isn't going to be changing in its mass, so what we're really looking at is the change in velocity of the particle as a result of the collision. When you're asked to calculate the impulse, you can use this formula here. So we're going to have a look at the mass multiplied by the change in velocity. It's really important that you think about which direction that impulse is acting in. So if, for example, we had two billiard balls that are aiming towards each other and they're going to collide, the impulse is pushing them out in opposite directions. So the impulse is always measured outwards from the collision. Second thing we're going to have a look at is conservation of momentum. You'll already have seen this in physics, I expect, but just to sort of make it really clear, the total momentum of everything involved in the collision, so if you've got two particles before the collision, that's the momentum of one particle and the momentum of the other, where u is the same as suvat, it represents the initial velocity, and it must be equal to the total momentum of all the particles after the collision, where v is our final velocity. You can of course extend this. If you've got three particles, you can add an m3u3 and an m3v3 term on either side. So here's an example of what we might be asked to do in M1. We'll be given this long-worded question from which we're going to draw a diagram. So to start off with, we've got a particle P of mass 2 kilograms, so I've drawn that here. And I know that it's moving with speed 3 meters per second on a smooth horizontal plane. Okay, so my direction is going towards the other particle, moving at 3 meters per second, and that's its speed before the collision. I'm also told that I've got particle Q of mass 3 kilograms, so I've drawn that on my diagram. And we're again looking out for those keywords. It's at rest, so its initial velocity is 0. You don't necessarily need an arrow here, you could draw it as a dot, but it's entirely up to you. Obviously it's got no direction per se, as it's not actually moving. Okay, next up we're told particle P collides with particle Q, so we know there's going to be an impact, and therefore straight away we know that we're going to have an impulse acting outwards from that collision. And afterwards we're told that Q moves off with a speed of 2/3 meters per second squared. Okay, so we've got this 2/3 meters per second squared. We know that it's going to this right direction purely because before it was at rest at its initial state, and then it was bumped from the left, so we know that the movement's going to end up going up to the right. Okay, so now we're going to have a look at finding the speed and direction of motion of P after the collision. Now, I'm not overly sure about the direction of the collision. It might be that Q was such a stopping force that P bounces back, or it might be that P nudges Q forward but then slows down, carrying on in the same direction. The way to tackle this is to choose a direction for your diagram, and if it comes out negative, then you can say that it's in the other direction. So I've started off by thinking maybe it's going to go to the right. Okay, so our conservation of momentum formula is m1u1 plus m2u2 equals m1v1 plus m2v2. After that then, we're going to start substituting in values and see what we've got left. So in this case, I'm going to call P my particle 1 and Q my particle 2. So mass of P is 2 times its initial velocity of 3. I've automatically assumed in this that my positive direction is going to the right, but may as well make it very obvious from our diagram. Then we've got plus m2, which is 3 times by its initial velocity of 0, and then we're moving on to the green section, which has our afters. So 2 times the unknown velocity plus 3 times 2 1/3. Okay, so at the moment everything's moving to the right, so everything is going to be positive. 2 lots of 3, 6 plus 0, so we've got nothing else there. 2v and 3 lots of 2 1/3 are going to give us 7. Rearranging there, I'm going to end up with minus 1 equals 2v, so that tells me that v is minus 0.5 meters per second. Okay, so it turns out I did pick the wrong direction, so what I can say instead, when I'm answering this question, I can say that speed equals 0.5 meters per second, because speed is only a magnitude, it's got no sign, and I would also say that the direction is, and you're going to have to come up with a way to describe this because it's difficult to call it the negative direction because we haven't really defined a positive from the words in the question, we chose that ourselves. So I would say that its direction is away from Q, and that's really making it implicit. You definitely can't say left or right because your diagram might be back to front to what anyone else has. Now we can have a look at part B, finding the magnitude of the impulse received by P in the collision. Okay, although it says the impulse received by P, there's absolutely no need to use P because we already know that impulse is equal and opposite, so it doesn't matter if we choose Q instead. And I would suggest that choosing Q would be a better option because just in case you messed up part P, you don't want to, part A using P, you don't also want to mess up part B. So we're going to have a look at the impulse of Q, and we're going to use our formula I equals mv minus mu. And I'm looking in the direction of my impulse, so I'm going to take to the right there as positive. Right, substituting in, I've got the mass of 3 times by its final velocity, which is 2 1/3, minus the mass of 3 times its initial velocity. So nice numbers here. I equals 3 lots of 2/3. Again, that's our 7, and our units are kilogram meters per second. If you struggle to remember that, it's purely the units that come from the question. So kilograms, that is our measure of mass, and this is our measure of velocity, and all we've done is mass times velocity in our formula, so you just put in those units together. Second question, I haven't put any information on the diagram yet, I've just set it up. So pause the video now, see if you can put all the information from the question on yourself, and then unpause to check it. Okay, so here's my completed diagram. I have put all the information on the diagram, so I've got particles mass of m and km, which are here and here. This speed 3u and 2u respectively, again you're remembering it's in the same order as the previous bit. So 3u for the m and 2u for km. Then we're having a look at the fact that they are travelling in opposite directions, which is why I've got them both going inwards, otherwise we're not going to have a collision. As we know that they collide from this, we're then told that as a result the direction of motion of both particles is reversed. So it was travelling to the left, then it goes right, travelling to the right, then it goes left, and their speeds are halved. So if we started with 2u, now we've got u, started with 3u, now we've got 1.5u. Okay, so now we've got to find the value of k. We're again going to use our momentum formula, so m1u1 plus m2u2 equals m1v1 plus m2v2. Before I start subbing in, I'm just going to make my positive direction nice and clear. Okay, so first velocity, this u1 is travelling to the right, so it's going to be a plus 3mu. Then we've got our second particle over here. Its velocity is going to the left, so we're looking negative this time. So it's going to be minus 2kmu. Then we've got our particle on the left travelling to the left as well. So it's going to be negative for this m1 section. So it's going to be minus 1.5 mu. And then for our last particle, we're moving to the right. So that's going to be a plus kmu. Okay, we've only got this one equation and we've got 3 unknowns. So either we need more equations or we need to look for a common factor. Thankfully we can find one. We've got m in every term, so they'll all cancel. And we've got u in every term, which will cancel as well. So I'm dividing by m, then dividing by u. Simplifying it to 3 minus 2k equals minus 1.5 plus k, and a little bit of rearranging gives us that 4.5 is equal to 3k, therefore k is equal to 1.5. Finally, we've got to write down an expression in terms of m and u for the magnitude of the impulse which P exerts on Q during the collision. Again, all of this extra bit, this P exerting on Q during the collision, is not important. All we need to worry about is just one of them. It's asked it to be only in terms of m and u, so either we can use our k value and have a look at the right-hand particle, or in case we made a mistake, I'd suggest you'd be better off using this left-hand particle here. So, impulse is mv minus mu. And I know that when I'm looking at my left-hand particle, I'm taking my impulse to the left. So I've got my mass m times by my final velocity, which is 1.5 in my new positive direction for impulse, going this way. And then I'm going to subtract the mass times by the initial velocity, which is going in the negative direction, so it's minus 3u. So a little bit of simplifying, we've got 1.5 lots of mu minus 3 lots of mu, so in total we've got 4.5 lots of mu. Okay, this one's very slightly different, in which it actually starts with having the two things together and then eventually they're going to split apart. So there's almost not a collision, they've almost collided before this has all started. So we've got a cannon of mass 600 kilograms. So we're going to have our cannon here, so 600 kilograms, and it lies on a rough horizontal surface used to fire a 3 kilogram shell horizontally at 200 meters per second. So initially, because it says that they are lying on a horizontal surface, the velocity of both of them starts off by being 0. However, after the collision, or rather after the firing of the cannon in this case, it's going to be moving horizontally at 200 meters per second for the shell. So the shell is going to fire away from the cannon, moving at 200 meters per second. We don't know yet what's going to happen to the cannon, but we can guarantee that if the shell is firing forwards, then this has definitely got to be firing backwards, otherwise there's no way we'll ever be able to conserve momentum. Impulse as usual, this one is being fired outwards and therefore this one is recoiling backwards. Okay, first up then, we're finding the impulse which the shell exerts on the cannon. Ignore all of the what exerts on what, we know they're equal, so let's pick our easier scenario with the actual values in it, which is for the shell. So impulse equals mv minus mu. So we've got 3 times our final velocity of 200. I've got my impulse direction on the diagram, but I'll just write it here to be safe. Minus the mass times by 0. So nice and easy, 600 kilogram meters per second for the impulse. Secondly, we've got to find the speed with which a cannon recoils, and for this we're going to either want to use our conservation of momentum, or now that I know the impulse I could use that instead, and I'm going to show you how you'd use that now. So we might instead do the impulse for the left-hand particle, i.e. the cannon, and that's going to be going in this direction. We know the impulses are equal, so this has to be 600 as well. The mass starts off by being 600, and it's a final velocity that we don't know, and it's 600 times 0 because its initial velocity was 0. Rearranging, we'll end up with v being equal to 1 meters per second. The final example that we're going to have a look at is very slightly different to the others, purely because it says that we're going to have to be finding the common speed of the particles after this string becomes taut. And this is the first time where we've had two of the particles travelling at the same velocity because they're connected in this case. So reading through, we've got two particles of mass 2 kilograms and 1.5 kilograms. So we've got 2 and then 1.5. They're at rest on a smooth horizontal surface. So we're going to ignore that bit for now. We're going to have a look at the fact that they are connected by a light inelastic string, which is initially slack, so they're not in any way related. And our before scenario is that particle P, which is our left-hand one, is projected away from Q with a speed of 7, whereas this one is starting with 0. We're then asked to find the common speed of the particles after it becomes taut. As one's moving to the left to start off with and the other is stationary, we know that the afterwards movement has got to be to the left here. It's a common speed, so we can use the same letter for it, and I'm going to use v because it's the after the final velocity. Okay, quick calculation with our conservation of momentum. m1u1 plus m2u2 equals m1v1 plus m2v2. Left-hand particle is going to be my 1, right-hand particle is going to be my second particle, and as everything's moving that way, let's make to the left the positive. 2 times 7 plus 1.5 times 0 is 2 times v plus 1.5 times v. Simplifying, we've got 14 equals 3.5v, which means that v is going to come out to be 4 meters per second. Then we're asked to calculate the impulse, very similar to what we've been doing so far. So I equals mv minus mu. Here you're going to have to use the velocity that we just calculated because you didn't know it for either before, but I'd be tempted to use my right hand particle here, q, as I've got 0 involved. So mass is 1.5 times 4 minus 1.5 times 0, therefore my overall momentum is going to be 6 units per kilogram meters per second.